Now the phase sequence. So phase sequence means the sequence of appearing phases. So we have three phases, A, B and C. So previously we have written it the voltages, like let me show you again. So here we have given you 0 degree at the first A phase, and we have written B phase as minus 20 degree. So why do we write it B as minus 20, not C as minus 20? So also we can write ECN, this should be another form. ECN is minus 120 degree and EBN is minus 240 degree. So this could be another representation. That's why the phase sequence came. So phase sequence can be either ABC sequence or ACB sequence. So let me show you ABC sequence. In case of ABC sequence, we can write EAN as the reference one, that is the angle 0 degree, and so the second one, that is the EBN, so this should be minus 120 degree. Since this is ABC, so first one A and second one will be B here, and the third one C, this should be minus 240 degree. Also you can write it plus 120 degree as well. So these are the phase components, and if you want to write the line components, so these are just equal. So EAB equal to EAB 0 degree. So these are the line voltage, and this is the line magnitude. So don't worry, because it is already multiplied, because we are writing it the line voltage magnitude. That's why. Now this is first one, that is EAB, and the second one should be BC, and third one CA, since this is ABC sequence. And if it was a ACB sequence, so if A is the reference, then C should be minus 120 degree and B should be plus 120 degree or minus 240 degree. And similarly these are the components. So EAB, then CA, then BC. So EAB, after EAB it appears as ECA as minus 120 degree, since ACB. So now the delta connected generator. So previously I showed you the Y connected generator, now the delta connection. So delta connection, that means it looks like delta. So whenever we have three phase, just like this one, this one, this one, so when we connect this one with here and this one with here, that means more of series connection. One end of first phase is connected to the first end of second phase, and so on. So this gives you a delta connection. If you notice, AB, then BC, then CA. So this gives a delta connection, and in case of delta connection there is no neutral point. Anyway, so in case of delta connection we have 3 points, A, B and C. So we have connected a 3-phase load in these 3 terminals. So this is line A, line B and line C, and these are the line components or the phase components of voltage. So in case of delta connection, the line voltage and phase voltage are equal. So let me show you. So let's say this phase's voltage, that means I can say EAN, similarly for Y connection. So this is the phase voltage, and if you notice, this portion is connected, right? So from A to B, this EAN is being supplied. So I can say that EAB is just EAN if I write EAN as the the phase voltage. So in case of delta connection, the line voltages and phase voltages are equal. Similarly, if you notice in this phase, that is BC, so this BC is connected in this point B and C, right? So obviously this voltage, that is the phase voltage, if we call it BN, it is equal to BC. So in case of delta connection, line voltage and phase voltages are equal, but for current they are different, because this is the line current, let's say IAA. So A, that means this point, and we can call it, this is A point, small a, and this is B and this is C. So this is IAA, this is IBB and ICC. So this IAA, you can understand that this current here, IBA is in this direction and IAC in this direction. So obviously you can apply a Kirchhoff's current law, and then you can identify the value of IAA. And obviously this is not directly equal to IAB or ICC. CA. So that's why the line current and phase currents are different for delta connection, but the voltages are equal. So now again we can say these are the phase voltages, and also these are the line voltages. So for line we generally write it A, B, B, C, C, A, but for phase we can write it A, N, B, N, C, N. Although there are no neutral point, but to demonstrate the phase component we can write it. So now if we want to derive the expression for current, again the voltages are equal for both line and phases. Now for the current, so at node A, if we want to write the Kirchhoff's current law at that node A, so you can understand that this current is entering, that means IBA is entering and other currents are leaving, so IAA plus IAC, these are leaving, right? So from here we can write IAA equal to IBA minus IAC. So we can write it. So from again we can draw the similar vector diagram where we can derive the expression. So this is I just shown you, and now again we can draw the phasor diagram or vector diagram. So these are the three phases that are displaced 120 degree from each other, and then we need if you notice here we need BA plus CA. So we have already BA just like this, and we have AC in this direction, so CA should be in the reverse direction. That's why this is the CA, and again this is the 60 degree direction, just like our derivation of voltages in case of Y connection. So this is the 60 degree, and again this has the same magnitude, so obviously the resultant current will be at 30 degree angle. And in similar manner we can derive the expression, and we will got just like this. That means our line components will be √3 times of our phase components. And another thing here, if you notice, we got the resultant, that means the line is minus 30 degree angle. That's why in case of the first phase, that is A phase, we have written it minus 30 degree, and for voltage it was plus 30 degree, if you remember. So that's why IAA we can write minus 30, and similarly the second one, previously it was minus 120 degree and minus 30 is added, so obviously now it is minus 150. And third one you can write it either 240 or plus 120 degree. So if you write it plus 120 degree for third phase, and now it is minus 30, so the resultant will give you 90 degree angle. So these are the expressions. So now if you draw them, so this is just the phasor diagram of both line component and phase components of current. So first of all, if you notice, the magnitude are larger since this is multiplied by √3, so obviously this line component are larger, that's why they are shown at a larger distance, and they have a minus 30 degree phase shift. So corresponding to IBA phase, we have the line component IA that is at angle of minus 30, and similarly corresponding to IAC we have ICC, and for ICB we have IBB. Now the load type. So previously we have showed here that we generally connect this three-phase system with three-phase load. So obviously there could be two different types of load. Either this could be Y connected, just like here it looks like a Y, three impedance are given. This could be various combination of resistance, inductance and capacitance, and similarly this could be delta connection. And then if these branch components are equal, that means if Z1 equal to Z2 equal to Z3, then we can call it a balanced load, and if they are unequal we call it unbalanced load. Now a YY system. So YY system, that means Y connected source is connected to Y connected load. So this is a Y connected source we have observed, and this is a Y connected load we have observed. So we have just connected corresponding terminals. That means A is connected to this A phase, both neutral are connected, and B is connected to B, and similarly C is connected to C. And then these are the phase components of voltages, all are written E phi, and these are the corresponding voltages available. That means the voltage drop at this load, so V phi, then here also V phi, and then these are the Z1, Z2, Z3, these are the corresponding loads, and the phase currents, that is here I phi Z, that means at generator side, and here I phi L, that is at load side, and this is the line component IL. And again, you know, there are phase components and line components. So for line voltages, let's say for AB, so this should be from A phase to from B phase. So let me clear it. So all I am saying that this AB line current, that means from A phase to from B phase, this should be ELAB, and similarly from A phase to from C phase, we can write ELCA. And similarly we have ELBC as well. So obviously for balance load, I already mentioned that all of these branch impedances should be equal, and you know that for YY connection, since it is Y, so obviously the currents all should be equal. That means this is the phase current at generator, this is our line current that is available from generator to load, and this is our load current. So if you again notice, this is our phase current that is being supplied from here, and this is available at line, and this is being supplied. So all these three are equal in case of YY connection here. And again, you can know that the line voltage is √3 times of phase voltage, and this portion is just showing V phi equal to E phi. That means the voltage supplied is equal to voltage available, since this is YY. So let me show you. So voltage supply, that means this portion E phi equal to V phi, because we have just connected A with A and N with N. So obviously this V phi, that means the voltage drop at Z1, this should be equal to the voltage generated E phi at branch A. So this is just written here.